longitudinal.
Sorry, go ahead. Yeah.
Yeah. So just to start again, I'll be presenting my thesis today on a study of explainable decision support for longitudinal sequential decision making. My chair is Dr. Subbarao Kambhampati, and my committee members are Dr. Erin Cho and Dr. Shailik Sengupta. So to start off, uh, let us look at a firefighting scenario in the city of Tempe. So firefighting is not just deploying engines to extinguish fires. There's a lot of logistics that is involved, starting from alerting the required authorities to addressing the media. Uh, there are a lot of things that need to be accounted for. Therefore, a plan is required. Now, in this scenario, imagine a firefighting chief along with a planner has to come up with a plan to extinguish fires. Now, the chief is an expert and has dealt with many fires. And the key points to remember here is that this fire chief is responsible for the final plan, and the fire chief is the one who has to execute it, whereas the planner supports this fire chief in making those decisions. Now, I've been saying we need a plan and there is a planner. So let's step back and first look at what exactly is planning. So sequential decision making or planning is the process of synthesizing the course of action to achieve certain goals. This has been of significant interest in the field of artificial intelligence for the past several decades. Now, the canonical view looked at planners generating a sequence of actions when a fully specified problem was given. So uh, essentially, all you had to do was give a fully specified problem with the initial state and the goal state and the complete action model to a planner, wait until cows come home, and voila, you have a plan. So, and research was mostly done to generate these plans faster and for more expressive problems, which accounted for uncertainty, partially satisfiable goals, temporal and durative actions, etc. Now, a crucial point that wasn't considered was the human in the loop. Now, human in the loop planning has become a necessary requirement because humans become an integral part of the planning loop. And there are several cases that arise when the human in the loop is considered. The first case is human aware planning, where the planner, along with its own capability model, has to account for the mental models of the human and plan accordingly. Another case is mixed initiative planning, where the user enters the land of planners and tries to manipulate the internal search process and help the planner make better plans. Now, this can be seen as a form of symbiotic autonomy where the user is trying to help the planner and the planner is essentially responsible for the final plan. Now, if you reverse the roles and if you let the planner enter the land of humans and help the human to make decisions, a new case that is known as decision support arises. Now, our scenario, our firefighting scenario, is is this case of decision support. So essentially, the fire chief is responsible for the final plan, and the planner is trying to help the fire chief come up with a plan. Now, the motivation for such systems also has roots in naturalistic decision making. So naturalistic decision making studies how humans make decisions in complex scenarios. So it essentially says that humans bring in a lot of experience and intuition to cope with challenging conditions. And the heart of NDM lies the requirement of letting this expert human be in charge and have an assistant help these humans. So using this as motivation, there is a proactive decision support system, which is known as radar, which essentially provides proactive decision support to aid the human in the loop. And it has been proven to make faster and better decisions. Now, the key functionalities in this system include hand coding plans. So the fire chief in our scenario can hand code plans. They can ask for plan validation and repair. They can ask for a new suggestion. And if the suggestion is unacceptable to the fire chief, they can also ask for explanations. Now, radar supports uh, plan explanations as model updates. So what it does is it takes into account the model of the fire chief and tries to present the relevant updates that are required in that model, so that the fire chief will understand why the plan that the system came up with is the best plan. Now, these explanations are not based on specific user queries. So what this might lead to is radar essentially is providing global explanations, and it's providing proactive global explanations, which might lead to the user having a hard time processing. So an alternative way to provide explanations is to let the human, expert human, drive the dialogue and question the system's decisions with an alternative, which we will refer to as FOI. So the fire chief can, instead of asking just why did you come up with this plan, uh, they can propose an alternative and ask why did you come up with this plan and not this alternative that I had in my mind. In response, I empower the system to provide contrastive explanations that are based on the user specified files. Now, along with that, if the fire chief is coming up with an alternative, we interpret that that alternative might contain some latent preference of the user, and we use that interpretation to provide better plan suggestions. And we do that using 3 different interaction strategies. And finally, we'll have we look at different evaluations where we demonstrate a working system that demonstrates the capabilities, and we have a computational evaluation for the use case, and we also have a user study to actually check whether users ask for contrastive explanations. And this essentially are the contributions of this thesis. Now, let us take a closer look and at the use case to illustrate the technical problems. So we'll represent our firefighting scenario as a classical planning problem, which is represented in PDDL. Now, a classical planning problem has a domain, an initial state, and a goal state. And the domain consists of uh, uh, a set of fluents which represent a state, and a set of actions which take from one state, which take you from one state to another. Now, this is a snapshot of an action represented in PDDL, which is planning domain and definition language. So uh, in this action, you can see there are this is a send social media action, which represents uh, uh, the fire chief trying to send a social media post. So, and for this action, there are a set of preconditions and a set of effects and a cost involved. Now, the assumptions that we make in our scenario is that the system has a model of the task along with the human, and these models might differ from each other. So the system has a model of how fires are extinguished, and the human has a model of how what the plan should be to extinguish a fire. And these models might differ from each other. And another assumption that we make is that this human's model is known to the system beforehand. Now, there are 2 possible goals that exist in this scenario. One is the extinguishing a big fire or a small fire. So we look at if the user wants to extinguish a small fire, right? And we look at the system generating a plan, suggesting a plan for extinguishing a small fire. And there are 2 parts that the user finds incongruous with their expectations. So the first part is the user wants to send out a social media post and address the media themselves. But the user is not aware that once posted in social media, the media will pick up the news from these forums and the fire chief does not have to address the media separately. Now, another part that is incongruous with the user's expectations is that the user expects that uh, big engines should be deployed along with small engines. So the user is kind of unaware that both types of engines cannot be deployed together. So this is technically represented as delete effects. So the delete effect of send social media is also a precondition for address media. So the actions send social media and address media cannot come together in the same order. And similarly, there is a delete effect of deploy small engines, which is called no engines deployed, and which is a precondition for deploy big engines. So the actions deploy small engines and deploy big engines can't come together in the given order. So uh, after the system suggests the plan uh, and the user sees that only one of the expected action pairs is there in the suggested plan, the user uh, will question the system and say, hey, why did you do this plan instead of these set of actions? So the user raises a file which contains the 4 actions in the given order. Now notice that the foils here need not be complete plans, right? So they can be, the foil here is a partial plan, which is a set of actions with ordering constraints. And these set of actions can be, can represent a set of candidate plans for the problem. Now, since the user has raised a foil and questioned the system, we'll look at how the system can provide contrastive explanations. So contrastive explanations are answers to the question to contrastive questions of the form why P and not Q, where P is the fact that is being explained and Q is the foil or the alternative that is specified. So here, the plan suggested by the system is being explained, and the user is trying to ask, why did you do this plan and not the set of actions that I expect? So the foil here takes, as I mentioned, takes a form of the partial plan where uh, it has a set of actions and ordering constraints. Now, the need for explanation arises when this specified foil is not part of a valid plan in the system's model, or is suboptimal or costlier than the plan suggestion. So if the set of actions that the fire chief provided is not part of a valid plan, then there is a requirement for explanation. Or if the set of actions lead to a suboptimal or costlier plan, even then there is a need for explanation. So we specifically look at the first case and try to provide minimally contrastive explanations for that. So how we do this is we search in the space of models with the below objective. So this objective, what it essentially tries is that it tries to find the minimal number of model updates that are required in the human's model, so that the human understands that the given foil is invalid. So we search in the space of models where given a set of foils that is raised by the human, the initial state is the human's model. From the human's model, we search in the space of models and find that particular model where no foil in the set can result in a valid plan. Now, uh, we do this by updating the human's model with a subset of model differences between the human's model and the robot's model. So this is similar to the minimally complete explanation search in the model reconciliation framework, which is the kind of explanation that radar provided. But there, the objective is to find a model where the system suggestion is becomes optimal. So essentially, they want to provide the model updates where uh, where when the model updates, when the human model is updated, the human understands why the system suggestion is optimal. But here we're trying to uh, 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 we're trying to invalidate the foil, and we're trying to make the user understand that uh, that the given foil is invalid by providing the required model updates. So essentially what we do is we start from the humans model, and we update the humans model with the subset of the subset of the model differences between the humans model and the systems model, and we compile the foil into this problem. So compiling the foil here means that in the new planning problem where the foil is compiled, any valid solution should contain the actions in the foil. And in this new planning problem, we check if this problem is unsolvable. So we rely on faster unsolvability tests that are sound but not complete. So we used in this work, we used a critical path heuristic test with the set size M in the initial states. So it essentially checks the reachability of the goal state, taking into account the interactions between fluents of sets of fluents of size M. So to ensure completeness, we iteratively increase the value of M until a solution was found. So once we check if the problem is unsolvable, then we present these differences between the updated model and the humans model as explanations. Now the human, when when the human takes into account these differences, the human will understand why the specified foil is invalid. So the explanation given for the use case is that the send social media action has a delete effect, no social media. So essentially now, once this particular update is accounted for in the humans model, the human will understand that, okay, these the set of the actions that I provided is not valid because send social media has a delete effect, no social media. So now, even though the human understood that, okay, the given foil is invalid, foils can actually be useful. So they can be as I mentioned before, they can be a possible indication of the user's latent preferences. Now you note that the action send social media and deploy big engines can be seen as the latent preferences of the user, because these were not mentioned in the plan, and the users specifically tried to ask why did you do these set of actions. So these can kind of be seen as the latent preferences of the user, and this can be used to provide better suggestions to the user. So you want to identify plans that are closer to the user's preferences, and we do this by 3 interaction strategies. The first interaction strategy is the nearest plan approach. So what do you mean by nearest plan is that it is you have to use the largest possible part of the specified file. So in order to do this, we revisit plan recognition methods and form a simple compilation where we encode the, the partial files as soft constraints. And if any of the constraints are violated, we impose a penalty. So essentially what we do is we augment the existing actions in the original problem with uh, 2 different actions. So for each of the observation, which are nothing but the actions specified in the foil, we augment 2 different actions. One is an explain action and a discard action. So an explain action is just a replica of the observation with an additional effect that ensures that the observation is met. And a discard action is a dummy action with a single effect where that also ensures that the observation is met but is discarded because the other effects have not been done. Now, the catch here is that the cost of this discard action is set very high and very much greater than the cost of the explain action. So what this essentially means is we want the planner to not discard any of the observations that are there, or any of the or discard any of the actions that are specified in the foil, right? So now, along with this, we add these met the predicates met o of I into the goals so as to meet all the observations. Now, for the foil raised, we can see that the nearest plan generated contains two of the actions. So it has the planner has discarded two of the actions. Now notice that this is a soft constraint because ultimately the planner can discard the actions, but it will cost more to do that. So for the file raised, you can see that there are two actions that are discarded and two actions that are explained in the nearest plan generated by the system. Now, this is fine if the user does not have any preference over the actions in the file. But if you can see, if as we said, as I mentioned before, deploy big engines and send social media can be seen as the latent preferences of the user, and the nearest plan generated did not contain these actions. So what we want to do is want to provide the user with the choice and ask them and try to elicit their preferences. So in order to do that, uh, what we do is we present the user with sets containing conflicting actions. So how we do that is we search the space of subsets of the file. So starting from the empty set, for each subset of the file, we compile the subset into a planning problem, and we check if the problem is unsolvable. So if the problem is unsolvable, that means no valid there can be no valid solution which contains the actions in this file. So we present these unsolvable subsets to the users and ask the users to sacrifice an action. So um, once the user sacrifices an action, we take the other action and try to present a plan which contains that action, right? So here, currently we preserve the ordering that the user mentions, so the permutations of sets are not considered. So in our example, we start from the empty set, we check each of the actions, and each of the actions, a plan can, the planning problem where each of these actions are compiled into have a valid solution. So um, then we check sets of two actions and we find two conflict sets here, and we present those two conflict sets to the user. Now the user can choose to sacrifice address media fire chief in the first conflict set and deploy small engines in the second conflict set. So once they sacrifice these two actions, we take the other two actions and provide a plan that the user prefers. Now, another approach to eliciting the preferences of the user would be to present the maximal valid subsets to the user as options to choose from. So what we do here is we present all the subsets which contain the maximum number of actions from the file with which a plan can be found. So we find all these combinations and we present all of them to the user as options to choose from, and then the user can choose what they prefer to get the preferred plan. So even this is we do a search in the space of subsets of the file, and starting from the entire file as a set, for each subset of the file, we again compile it into a planning problem. And first we discard those subsets where the problem is unsolvable. And if a plan can be successfully generated for that problem, we deem that corresponding subset as a valid subset. Now note that we do not check subsets that are already part of a valid subset, because we want to present the maximal valid subsets. So, and we present all the maximal valid subsets to elicit the user's preference. So here essentially, starting from the entire file as a set, we check which of these is valid, and we find these four different combinations of maximal valid subsets, and we present these to the user, and the user can choose one of them to generate a plan that they prefer. So here the user chooses big engines and address media fire chief, and they get a plan that they prefer. So, so far we have seen how we can provide contrastive explanations for if a user comes up with an alternative and questions the suggestion of uh, the system, and then we looked at how we can use these points and provide better suggestions that are closer to the user's preferences. Now we look at we look at evaluation of some of these capabilities. So first is there is a work. This is a working system which has also been accepted at AAA 2021. Um, so so this essentially this is a demo which demonstrates all the capabilities using a similar use case, and it showcases that this system is actually a working model and can be used by users. So then we have a computational, we performed a computational evaluation comparing the conflict sets approach and the plausible sets approach for the firefighting use case. So we looked at a single incongruous part, which is the send social media and address media. And it took 8.5 seconds to compute the conflict set and 9 seconds to compute the plausible sets. And when we included two of the parts, the conflict sets approach took 30 seconds and the plausible sets approach took almost the same amount. So this is due to, since the search is in the space of subsets, the for each additional action, the subsets explode combinatorially. So we so essentially uh, uh, it is kind of an expensive computation because it's a breadth first search in the space of subsets. Now, along with that, we looked at a user study to actually see. Of course, we do have uh, an algorithm and a working system, but we should also. But it's also important to see whether users ask for contrastive explanations. So what we did is we conducted a user study that looked at user preferences over two different explanatory questions, where the two questions were why the system came with this plan, which is the sort of explanations that were provided in radar, and why the system not come up with the plan that the user chose, which is the contrastive explanation that we are providing. Now, in order to test this, we first primed the participants on a simple domain, which is the logistics domain. So we essentially explained the domain to the user and created a scenario where they understand that uh, uh, they have to come up with a plan, and they have a system that helps them come up with a plan, and the models might differ from each other. So we explained the domain and the setting to the user, and then we gave a test to make sure of the user's knowledge level. We gave a questionnaire that asks questions about the task and to gauge the user's knowledge level. And then we presented a problem instance and asked the user to choose from the options provided. So they had to come up with a plan, and they had to choose from the plans that were given to them as options. And once they choose the plan, we provided the system suggestion and asked whether they would accept it as a plan, or whether they would want an explanation. And if they wanted an explanation, uh, then we had asked them whether they wanted to know why the system did not come up with the plan that they chose, or whether why the system came up with the specific plan. So once the required explanations were provided to the participant was also asked whether they require additional explanations, or was the explanation that was provided was enough to accept the plan. So we had 35 participants, all of whom were graduate and undergraduate students, and 32 asked for explanations, and 3 did not. So out of the 32 who have asked for explanations, 63% asked for a why question, and 38% have asked for a why not question, or asked for contrastive explanations. So what this essentially showcases is that a non-trivial percentage of participants have asked for contrastive explanations, and uh, this emphasizes the need to have or to provide contrastive explanations to users. And this is on a domain where the participants really do not have a real stake, but in real life scenarios, this could very well be the case that users would want to have contrastive explanations. Now, Another interesting insight that we found was, since we also asked whether the explanations were enough to accept the plan or additional explanations were required, we saw that a higher percentage of participants accepted the plan when the explanations were broken down as opposed to when they were presented with all the model updates. So when we presented a contrastive explanation and then they asked for an additional explanation, the users seem to have accept higher percentage of participants seem to have accepted the plan. So what this essentially showcases is that the contrastive explanations can be useful in making the user understand the system in a better way.
Karthik, one quick question. So for the contrastive explanation plus additional explanation, what is that scenario here?
Right. So for the contrastive explanation, we have essentially right. So we have planted two model differences, and for both the model differences, if you ask for a Y question, just a Y question, then you would be presented both the model differences. If you would ask for a contrastive explanation, since we are just invalidating the foil, we'll be presenting one explanation, and then they will be asked whether they want an additional explanation or not. So when they ask for an additional explanation, we provide the second update as well. And when we did that, the users seem to have accepted the plan. Higher percentage of participants seem to have accepted the plan, as opposed to when we presented.
So basically, in the graph that you have, the CE indicates where you provide just one explanation. The C plus additional explanation shows where they have asked for the second one, and MC is basically the case where they don't ask why not question.
Why not? They ask for why, and we present both the model updates.
Okay.
Right. So that was an interesting insight that we found, and so finally, as in the thesis, we've also placed the components of RadarX in in the degree of automation ladder, and you can see that the red parts, which are there here, are placed in the lower degree of automation, and that is essentially to facilitate naturalistic decision making, where the heart of it is to let the human be in control, and with the system supporting the expert human. So this essentially is how. So finally, in summary, we kind of looked at a bunch of things. We looked at how do we provide contrastive explanations by letting the user drive the dialogue, present the foil, and how we can refute the foil that the user presented using model space search. Then we also use the specified foil to generate and to identify and generate plans that are closer to the user's preferences. And we illustrated these capabilities with a use case scenario. And we've also seen a working demonstration of the system with the mentioned capabilities. We've seen a computational evaluation on the use case that we have that I've mentioned. And finally, we've also looked at evaluated whether users ask for contrastive explanations to a user study, and we found out that yes, users do ask for contrastive explanations, and that emphasizes the need to provide such explanations in decision support systems. Now, in the future, we can test how the interaction strategies are helping the users, and we can also look at improving the scalability and trying to look at even more exciting and complex domains. So I'd like to end with telling that the major part of this work has been accepted and presented at two different venues. One is ICAP's Explainable AI Planning Workshop, and the other, and a system demo was accepted and presented at AAAI 2021. With that, I would like to end. If anyone has any questions.
Thank you, Karthik. So right now we can have, maybe you can go back to the summary slide just in case, so that people can remember what the thing is. Yeah, so then right now the floor is open for anybody to ask questions, including the audience. And of course, committee members can ask anytime.
Yeah, I had a quick question, Karthik. So uh, for the three things that you showed, where there was contrastive plus additional explanation, contrastive and MC, what was the percentage of people who asked for each of those?
Yeah, so you're asking for the percentage. So that was around 83 percentage, and who asked for like who accepted the plan, and
Right.
there.
No, so I guess my question was, so basically I'm guessing the first two bars that you have is the 30% of people who ask for contrastive explanations, and the last bar has the remaining 62% who asked for
Correct.
MC. So out of that 38, what was the percentage of people who asked for the first one versus the second one?
So yeah, so the so this even this percentage actually represents that. So 80% of the 12 people who asked for why not question have accepted the plan, right? So so 100%
Okay.
of the participants who asked for a contrastive explanation asked for additional explanations, and in that 80% have
I
accepted
see. I see. Okay. Okay. Also, did you happen to do any studies on like the quality of the explanations provided as opposed to whether they would say accept the initial plan?
Right. So the idea was the initial hypothesis, or the main idea here was to kind of test whether users actually ask for explanations, but the more or less the problem with subjective feedback was that I hope that's what you're kind of asking, as
Yeah,
to
yeah, yeah.
whether users actually like the explanations or not. So uh, the idea was that uh, when uh, when we provided the explanations, like some of the participants like they kind of did not get the setting, and there was some bad data too. So uh, essentially I kind of concentrated on the actual hypothesis that we wanted, which was to check whether users ask for contrastive explanations. So, there's you're muted.
Oh, sorry. So basically, you're saying that you use these questions to see if, in the end, the users would eventually accept the plan. So basically, the purpose of the explanations is to make sure that whether the user accepts or not. But I think that it would also be very interesting to see if some parts of the explanation made more sense to the user, if they would have it any other way. Like those could also provide very interesting feedback on how we can structure these explanations in the future.
So actually, a detailed account is already also in the thesis, where
Right.
I mentioned all this.
Right.
Karthik, I know you and I have talked about the user study more extensively, so it was really nice to hear some of the first half of your presentation, talking about some of the technical justification behind it. I was wondering if you could elaborate for maybe the audience here listening to you, some of the challenges you encountered with the user study and what you would do differently for future studies.
Yeah. So the major challenge that that I encountered for this user study was that, as I said, some of the participants did not realize the setting, and the explanations that we provided actually helped them realize that the system's model might be different. And in fact, the participants also questioned as to why the system has these different rules, and that kind of also motivates one of the it also kind of motivates one of the key elements in contrastive explanations, where uh, just a second, we give an option for the human to veto the the model updates. So if the human truly believes that the system is at fault, right? So such kind of like the major problem that was encountered in the user study was that the participants failed to recognize the setting, and and in a way it's kind of similar in the real world scenario, where the all the user cares about is to uh, uh, to focus on the task, right? They don't really know, they might not know the setting, that the meta elements of uh, uh, the, uh, the meta elements that they're in. And when the explanation is provided, that's when they realize, oh, the system has a different model than their own, and this is how the system might have been thinking. So that was that was as much as a problem, but also an interesting thing that we found out in the user study. Yeah. Sorry about that. Yeah, so this is the part where the human can veto the model update that is presented by the system. And in the user study, we found out that some of the participants were kind of really shocked that the user had a different the system had a different model. And in those cases, that kind of motivates for them. They probably would have changed the planner's model, and this particular element would be a key factor there.
So maybe slightly related to that, but at a more higher level, earlier you talked about the importance of mental models, and then you also discussed expectations. Are you differentiating between the two, or what's the relationship between mental models and expectations?
I'm sorry. So you're asking about mental models and expectations. Did I heard that right?
Yeah, you talked early about mental models, and then a little bit sort of in the middle about user expectations. And I was wondering if you meant the same thing by those two terms, or would you differentiate them?
So yeah, in a way it's kind of the same, but the point here is that we can also look at it this way. So even though the user has a certain mental model, it's the inferential capability of the human need not be need not be as good as the planner. So the because of that, the expectations and the mental models might kind of differ with each other, right? So uh, the the mental model is essentially a representative of what the human's beliefs and expectations are. But if the inferential capability is not as good as the planner, maybe there might be a small mismatch in that.
Okay. Other questions? If the audience do not have any questions, then right now, anybody who's not on the committee or the candidate, please leave the Zoom meeting. Okay, so it's just the committee.
Stop the recording.
Yeah, thank you for reminding me. Okay, so I